In this video, we're going to continue talking about the topics of section 3.1 from the textbook. Now we are going to proceed to learn about what is the group number and what are valence electrons in an atom. We ended the previous video looking specifically at electron configurations and trying to determine what are the positions of the electrons in atoms. When it comes to group numbers and valence electrons, now we are going to focus on representative elements. Remember that representative elements are going to be the elements that are present in groups 1A through 8A, meaning that is going to be group 1A, 2A, all the way to 8A. So when it comes to the other notation that the periodic table has, is only groups 1, 2, and 13 through 18. So atoms have all different electrons. Now, valence electrons are going to be the electrons that are specifically in the outermost shell of an atom. In other words, they're going to be the electrons that are in the outside of the atom. So how do we determine that an atom has valence electrons and how many? Well, utilizing the concept of electron configurations, I am going to copy the information that we have specifically here for silicon. And I'm going to introduce it onto the slide. We learned that silicon specifically is going to have 14 electrons total. When it comes to the valence electrons, specifically for silicon, there are two ways to determine it. One way to determine it is that if you look at the electron configuration for it, you are going to identify the electrons that are in the outermost shell. The outermost shell is going to be the largest digit before the orbitals that we have overall in our electron configuration. So what I mean by that is that if you look here, we have some electrons that are in the 1 area. We have some electrons that are specifically in the 2 energy level or area. And then we have lastly some electrons that are on the 3 area. So the ones that are in the outermost shell are the ones that are in the area 3, or the energy level. Another way to view it is just the period number. So if I highlight those electrons specifically, I can see that overall, if I add the superscripts, 2 plus 2, that means that silicon is going to have 4 valence electrons. Now, if you look closer at a periodic table, understand that silicon is actually an element that when it comes to group number, even though it's not represented here, I'm going to write it in, is group 4A. By looking at the group number of representative elements like silicon, because it is in group 4A, it has 4 valence electrons. So that's the other way that we can illustrate it. So let me just write it down. Since silicon is in group 4A, it has 4 valence electrons. And as you can see, the number before the letter A gives you the number of valence electrons. So any atom that lives in column 1A has 1 valence electrons. 2A, 2 valence electrons. 3A, 3 valence electrons. 4A, 4 valence electrons. 5A, 5 valence electrons. All the way to 8A, 8 valence electrons. But note that helium at 8A is an exception to the rule, because when we look at the electron configuration for helium, it's going to be 1s2. So that means that helium out of 8 is the only atom that only has 2 valence electrons in its outermost shell. Everybody else has 8. Now, these valence electrons are very important. And we're going to see later how the valence electrons is actually what is transferred between atoms or is shared between atoms to make compounds. So for now, understand that those valence electrons for an atom is going to be, or it can be represented by dots. And an electron dot symbol or a Lewis structure can be utilized to represent those electrons. So as you can see here, aluminum has 3 dots because overall, if you look and explore the periodic table, aluminum is in group 3A. So it has 3 valence electrons. And that's how we represent it by the 3 dots. If we were going to do the Lewis structure for silicon, we put the symbol, and then we put 1 dot, 2 dot, 3 dots, 4 dots to represent the valence electrons that it has. Now, another type of notation that could be utilized in order to describe elements in the periodic table is the noble gas electron configuration. Noble gases, as I just mentioned, have 8 valence electrons except helium. And when we have the full electron configuration for an element, understand that we can actually shorten it to represent specifically the noble gases that are represented within a full electron configuration. Understand that overall noble gases are especially not reactive. And the reason why they're not reactive is because their electron configuration are especially stable because they have full energy levels of electrons, and they don't want to disturb that stability, because if you do, a lot of energy is released. So that's why for the most part you see that the noble gases are going to be, essentially not reactive. So what is the noble gas configuration? A noble gas configuration is going to be, as I just mentioned, a shorthand method of writing an electron configuration. So let's take, for example, here, the noble gas configuration that can be derived for a specific atom. And here we have sodium. So if we look at the full electron configuration for sodium, which has 11 electrons, because its atomic number, which we can see right here, those 11 electrons in sodium live in specifically the areas 1s2, 2s2, 2p6, 3s1. Now, within the full electron configuration for sodium, we can actually observe that there is part of that can be shortened by just expressing that neon shares 1s2, 2s2, 2p6 as its electron configuration. So we can take this portion of the electron configuration represented as neon in brackets, because that section of the electron configuration that I put in parentheses corresponds to neon specifically, and then outside of that we can put the rest of the electrons for our atom. Let's actually do one more example utilizing the element that we have been working with so far. So let's actually look at the information that we have for silicon. So let me just copy the information. And let's see how we can write the noble gas configuration for silicon. So when it comes to silicon, we can observe that overall there's part of it that it is similar to sodium, is represented by a noble gas. Also, in the case of silicon, we have neon as the noble gas that can be shorthanded in terms of the full electron configuration. So when we look at the full electron configuration of silicon, we can see that what I placed in parentheses refers to neon. And because it's not that silicon is neon, it's just that those electrons populate some a place in the atomic structure that is similar to neon's electrons. Then we put the rest of the electrons outside the neon brackets. So we do 3s2, 3p2, and we can observe that this is the noble gas configuration for silicon. Now, if we look at a periodic table, so you can utilize it as your reference. We observe that silicon is right here. And whenever we're doing noble gas arrangements, understand that you have to utilize the noble gas that precedes your element. So since silicon is right here, if we backtrack our boxes, meaning that we go, okay, from here, we go here, we go here, we go here, then we go to the second level. Neon is the last noble gas that we have here that is before silicon. So that's why it's noble gas arrangement. We're going to do it from the perspective of neon. It's going to be incorrect to actually put helium in brackets and then proceed with the rest of the electrons. So for example, let's say that we do one more example. Let's say that, for example, we take calcium. If I write the full electron configuration for calcium, make sure that you practice at home. Calcium, which lives right here, because of its atomic number, has 20 electrons overall. Those electrons are found in 1s2, next 2s2, next 2p6, which are these, 3s2, which are these electrons, followed by 3p6, which are these. And lastly, 4s2, which you can see are the boxes that lead us to calcium. To corroborate that I have the correct electron configuration, I can take 2 plus 2, that's 4, plus 6, that's 10, plus 2, that's 12, plus 6, that's 18, plus 2, that's where the 20 electrons for calcium live. Now, taking this information and then I want to do the noble gas arrangement for it, we can observe here that overall, we can see since calcium is here, the noble gas that precedes it is argon. Argon is going to be present in this electron configuration from here all the way to 3p6. Verified at home that that is the correct electron configuration for argon. So what I placed in the box, we can shorthand it and say in a bracket, that corresponds to argon. Outside of argon, we have 4s2, and those are the electrons that overall encompass the atom calcium. Make sure that you practice doing the full electron configuration, that you are able to determine the noble gas arrangement for an atom. And additionally, that you understand what are the valence electrons in an element given a full electron configuration in a problem.